Welcome all of you. In the previous lectures, we have discussed the transient stability analysis with the help of equal area criteria, and we have seen two applications as well. One is when there is any change in mechanical input, what happens to the stability. The second one is when regarding the fault clearing. When the fault is cleared at a particular angle, how it affects the stability, transient stability of a system. In that context, we have discussed about the critical clearing angle as well as the critical clearing time. Now, in today's lecture, we will be discussing some tutorials concerned to the critical clearing angle and time, as well as some simple problem that has been asked in the previous year university questions. Again, now here consider one question. It's a previous year, it's asked in 2015, not in the year syllabus, but in the previous syllabus. So again, the question is this: a 50 Hz 4-pole turbo generator rated 100 MVA 11 kV has an inertia constant of 8. Inertia constant means H. First question: find the stored energy in the rotor. Stored kinetic energy. Stored energy you are asked to calculate. Frequency is given, rating of the machine is given, number of pole is given as 4, the voltage is given as 11, inertia constant is given as H. You are asked to calculate the stored energy. So stored energy is nothing but stored kinetic energy of the system. How will you calculate the stored kinetic energy of the system? You have two equations. Kinetic energy is equal to half J omega S square, or otherwise, you remember that equation. Stored kinetic energy, H is inertia constant, which is equal to stored kinetic energy divided by rated MVA. From this we can calculate what is the stored kinetic energy, which is H into rated MVA. That is H into G. H is given as 8 and G is given as 100. So your stored kinetic energy is 100 megajoule. Now the second question, if the mechanical input is suddenly raised to 80 megawatt, that means your mechanical power PM is equal to 80 megawatt. For an electrical load of 50 megawatt, that means your PE, electrical power PE is equal to 50 megawatt. Find rotor acceleration. Rotor displacement is represented by delta. If displacement is delta, how will you calculate as acceleration? It would be d square delta by dt square, right? So neglecting mechanical loads. So here you are given PM, you are given PE, you are asked to calculate d square delta by dt square. How you calculate d square delta by dt square? Or is there any relation which relate d square delta by dt square, PM and PE? Yes, our swing equation. What was our swing equation? Our swing equation was m into d square delta by dt square is equal to Pm minus P, or h by pi f into d square delta by dt square is equal to Pm minus P. Now from this we need to calculate what is d square delta by dt square. Pm and Pe is given, whereas m is not given. But we know that m is equal to h by pi f, or gh by 180 f or pi f. Okay, so we can calculate m. So here there is no g because here it was in per unit. Here there is g because here m is not in per unit. Okay. So finally you can calculate d square delta by dt square is equal to Pm minus P divided by m. Okay. So that was a simple question. Now next third one. If the acceleration calculated is mentioned for 10 cycles, so time is given as 10 cycle, find the change in torque angle. That means d delta you are asked to calculate, and rotor speed, that is d delta by dt, and torque angle change means delta, rotor speed means d delta by dt at the end of this period. Now let's see what is PM. What is given? 10 cycle. What is 10? What does it mean by 10 cycle? It would be 0.2 second, because we know that 50 hertz means that is one cycle you have 20 milliseconds. So for 10 cycle you will be having 0.2 second. And we also have d squared by d delta square is equal to 337.83 from this here. So I can write d square delta will be equal to this thing. Okay. Now the change in torque angle is d delta, or that is the velocity. It is d delta, which is equal to 1 by 2 into this thing. Okay. So finally you'll be getting it as 6.75 electrical degrees. So this was a simple question which was asked in a university question. Now we are moving on to a second question. it is given a 50 Hz 4-pole turbo generator rated 40 MVA 11 kV has an inertia constant 15. Determine the kinetic energy stored in the rotor at synchronous speed. Determine the acceleration and torque. Then rotational loss is 20 megawatt and electrical power is 15 megawatt. Okay, so here everything in this previous question it would be similar. In the same case, the first question is kinetic energy you can calculate as G into H, like what we have done in the previous case. Okay, now to find the acceleration, the same thing, d squared by delta is equal to Pm minus P. Here Pm is given as 20 megawatt and P is given as 15 megawatt, same thing. And accelerating torque, torque is we are asked to calculate. Accelerating torque means accelerating power divided by omega Sm. So accelerating torque is, accelerating power is Pm minus P, right? And omega means 2 pi F into 2 by P, because here it is given in mechanical degrees, here we need in electrical degrees. That is the only difference. That's such a simple question. Now here comes our real problems in critical clearing angle and critical clearing time, and this was asked in 2015 university. A generator operating at 50 Hz. Okay, here onwards we can analyze the question. A generator operating at 50 Hz delivers 1 per unit power. So it delivers 1 per unit power means electrical power generated is 1 per unit power to an infinite bus through a transmission circuit in which resistance is ignored. If the fault takes place, reducing the maximum power transferable to 0.5 per unit. That means P maximum is equal to 0.5 per unit. Whereas before fault, this power was 2 per unit. That means when fault occurs, your maximum power transfer is 0.5 per unit. But before the fault, the maximum power was 2 per unit. And after the closure of the fault, it is 1.5 per unit, which means during fault the maximum power was 0.5 per unit, before fault the maximum power was 2 per unit, after fault the maximum power was 1.5 per unit. By the use of equal area criteria, determine the critical clearing angle. So while solving these kinds of problems, we should have a thorough concept of the critical clearing angle, equal area criteria, as well as the power angle equation. Do you remember the power angle equation? Yes, power angle equation PE is equal to P max sin delta, where PE is the electrical power transfer, P max is the maximum power transfer, delta is the load angle. How will you calculate P max? P max is equal to E into V divided by X, where E is the sending end voltage, V is the receiving end voltage, and X is the reactance between the transmission line. Okay. Now here in this question, if we clearly observe this question, it is clear that there are three cases. One is the situation just before the fault, then one is the case during the fault, and another one is the case after the fault. Okay, so let's start the problem by assuming three cases. Case 1, pre-fault, just before the occurrence of fault. Case 2, during fault, during the fault is occurring. Case 3, post-fault, what happens once the fault is cleared. Now these are the given values. F is equal to 50 Hz. PE is equal to 1 per unit. You can write it as PE0 because it was the initial condition or the stable condition. So I can write electrical power initial or the stable, which is given as 1 per unit. So during stable condition, we already discussed that electrical power is equal to mechanical power. So I can write mechanical power PM is also equal to 1 per unit because electrical power during stable condition is given as 1 per unit. Okay. Now it is given P max 1 means first case. Before the fault, the maximum power given was 2 per unit, and P max 2, that means 2 means during fault. Maximum power during the fault, it was 0.5 per unit. P max 3, that means third case, post fault condition, where the maximum power after the fault was given as 1.5 per unit. So these are our assumptions, like we are assuming these three cases, and these are the values given for the three cases, and these are the values given as the data. Okay, now let's proceed with the problem. Before proceeding the problem, we need to draw the power angle curve for the three different cases. That is, one is the pre-fault condition, post-fault condition, and during fault condition. Now only draw this power angle curves for the three different cases. Now for that, what was our y-axis? Our y-axis is power, electrical power, okay, and our x-axis is delta. This variation is delta same for all the three cases because delta can be varied from 0 to 180 degree. Okay, and now we will see what is the electrical power given. Mechanical power given. Mechanical power we have calculated it as 1 per unit. So I have drawn a straight line over here which represent mechanical power, which is also the same as electrical power initial. Now, how will you draw the curve? In order to draw the curve, I need the starting point and the ending point. It is obviously known to us because the starting point here will be 0 degree and here the finishing point here it will be pi radian or 180 degree. Now, what we need is our peak point. Once you get the peak point, you can easily draw the curve, right? Now, first we will draw the curve for the pre-fault condition. In the pre-fault condition, the maximum value is given as 2 per unit. Okay, so you can mark in the scale a 2 per unit. Now by joining all the three, you can draw a curve like this, and this curve represents the power angle curve for the first case, that is pre-fault condition. Okay, now we need to draw the curve during fault. During fault, the maximum power is given as 0.5 per unit. So you can mark a 0.5 per unit in your graph and the corresponding value, and correspondingly you can draw a curve where this curve represents the power angle curve during fault. Now another one more curve is pending, that is post fault condition, where the maximum power is given as 1.5 per unit. That means by considering that the maximum value, by considering that maximum value, you can draw another power angle curve which represents the post fault condition. Okay, which represents the post fault condition. Okay, clear? So in this way, first you need to draw the three curves and the mechanical power input. Now let's mark the different operating regions. Now tell me, in which region our machine was operating initially, or at which point our machine was stable? We know that the machine is stable when the mechanical power is equal to electrical power. That is, we are discussing the pre-fault condition. Okay, fault has not yet occurred. So PM is equal to PE. So this is our PM curve, and pre-fault condition curve is this big one. Okay, now its meeting point, this would be the meeting point, or this is the point at which mechanical power is equal to electrical power, right? So that let that be our operating point A, and the angle corresponding to that is actually delta 0, okay, or initial load angle. Okay, clear? The machine was operating like this. What happened suddenly? Suddenly a fault occurred. When fault occurred, what happened to our power angle curve? So our power angle curve is no longer this curve. Which is our power angle curve? Case 2. This would be our power angle curve, isn't it? During fault. Okay. So your operating point shifted from this point towards, will it reach 0? No, because during fault you have another curve over here. So this will be the new electrical power, isn't it? And let that operating point be. So this will be your new electrical power. Now you can see that your electrical power is less compared to your mechanical power. Mechanical power is 1 per unit. Now the electrical power here, it is approximately less than 0.5 per unit. So what happens? Your machine will start accelerating. Okay, so the machine start accelerating means your rotor angle increases. Your rotor angle increases and it go on increasing, and you assume a point or assume an angle, that is clearing angle, at which fault is cleared. Once a fault is cleared, what happens? Your electrical, now this is not your curve. Now the curve is this post fault condition. So your operating region shifts from this point to this. Will it move to this point? No, it will not move because it was the pre-fault condition. Now this is our post-fault condition. So it will reach over here. Okay, so due to inertia of the motor, the load angle continues to increase. Finally, it reaches this point beyond which it cannot increase. Okay, and let that value be delta max. Okay, so now you got different values like delta 0 is the initial load angle, delta CR is a critical clearing angle, delta max is the maximum value of the load angle. Okay. Now, for this system to be transiently stable, what is the condition? Accelerating area should be less than your deaccelerating area, or your accelerating area should be maximum equal to your deaccelerating area. Now, which is your accelerating area and which is your deaccelerating area? Accelerating area means Pm minus Pe. From which angle to which angle the machine is accelerating? Delta 0 to delta CR, your machine is accelerating, right? Machine is accelerating. Okay. Now, what is the area? Pm minus Pe. Which is a Pm? The straight line represents the Pm. Which is the Pe? This is the Pe, isn't it? During fault, this is the curve. So the area is this one, marked, this area. Pm minus P between the limit delta 0 to delta CR. This is our first area. Now, which is our deaccelerating area? The motor will be deaccelerating from this angle to this angle, right? And that is PE minus PM. So, this is the curve PE and this is the curve PM. So, this area, that is between delta CR to delta max. So, these two areas should be equal. Okay. Now, let's see which are the two areas that we have discussed here. Discussed here, these two areas. Now let's see which are the those two areas. First area is delta 0 to delta CR PM minus PE, second case, into D delta. And area 2 is delta CR to delta max, that is third case power minus PM D delta. Now we know that PE is equal to P max sin delta. So PE second case is equal to P max second case into sin delta, and PE third case will be equal to P max third case into sin delta. Now, what is, we already know, right? What is this P max 2 and P max 3? We already know. Now, from this case, now from this curve, how can you write what is the value of delta max? This value is pi, isn't it? So, delta max is equal to pi minus this much, isn't it? Observe the curve, pi minus this much. And what is delta 1? What is delta 1 actually? Here, what is delta 1? This point, right? This point. Okay. At this point, what is your electrical power? Is equal to 1 per unit. So, by keeping that into consideration, I can write delta max is equal to pi minus delta 1. So, from the power angle curve, I can write P max 2 sin delta 1 is equal to 1 per unit, or PE is equal to 1 per unit. From that, I can write delta 1 is equal to sin inverse 1 by P max 3. I mean P max 2. What is it? It is 1.5. Okay. So, you will be getting it as what? 41.8 degree or 0.728. I mean 729 radian. Okay. And this is P max 3 actually. Okay. So, you got the value of delta max also. Now, what is delta 0? Now, from this, what can be the value of delta? Sorry. What can be the value of delta 0? Delta 0 means this value. Okay. So, or I can say that this value. So, this value means your electrical power is equal to 1. So, P max is, what is the P max? Here 2. P max sin delta 0 is equal to 1. So, from that you can calculate the value for delta 0. Similarly, okay, you got the value of delta 0. Now you can equate the two areas. Area 1 is equal to, it is from delta 0 to delta CR, this. So same integration, and we know the values, all the values here. Now you got two areas over here. On solving, you got two areas. And for the system to be stable, what is the condition? Those two areas should be equal. Now while equating this, you'll be getting the value for critical clearing angle. You'll be getting it as 70.3 degrees. So you please work out this problem. Unless you work out this problem, it will not be clear to you. So you just work out this problem, and if you have any doubt in any steps, please return back or revert back or comment it. Okay. So you yourself solve this problem. All the hints and some notations, everything is provided in this lecture. Along with this, I'll be providing you the material as well. So kindly go through it. Okay, and here the only logic of the theory we need to know is regarding the equal criteria, how you draw a power angle curve and everything like that. Okay, you just go through this problem, work out this problem, and these type of question has been asked in the previous university questions, not in this syllabus. So in this particular syllabus, such problems are not yet asked, but there are chances for this type of questions. Okay, now we will be proceeding to the next question, which is very similar to the previous one. So if the previous question is clear to you, it will be easy for you to understand this problem. Consider the system shown in figure where a three-phase fault is applied at a point P shown. Okay. Here sending in voltage is given as 1.2 per unit, receiving in it is given as 1 per unit. Then reactance is also given. Find the critical angle for clearing the fault with simultaneous opening of the breakers 1 and 2. The reactant values of various components, everything is indicated. The generator is delivering 1 per unit power at the instant preceding the fault. Preceding the fault means just before the fault, the generator was delivering 1 per unit. That means during stable condition, the generator was delivering 1 per unit, which means mechanical power and electrical power are same, which is equal to 1 per unit. Hope it is clear. Okay. Now let's analyze the three condition. What is the three condition? Pre-fault, during fault, post-fault. Now let's analyze the pre-fault condition. This is a case, right? This is a case. So the effective reactance, we know how to calculate this effective reactance. You got the effective reactance. Sending end voltage is given as 1.2, receiving end was given as 1, and total reactance now calculated as 0.522. So you can calculate the maximum power, and so you can write the equation. That is maximum power during pre-fault condition is 2.29 per unit. So you can write PE first case, that is pre-fault case, is equal to 2.29 into sine delta. Now during fault means the fault occurs like this. So no power is transferred. That means electrical power is zero in the case during fault. Okay. Now let's see post-fault condition. How is the post-fault condition? These two breakers are opened. So that means this reactance will not be there in picture. So the effective reactance will be 0.25 plus 0.5 plus 0.05. Sending end voltage and receiving end voltage remains same. So the maximum power is sending end into receiving end divided by total reactance. So the maximum power you got it as 1.5 per unit. This is after fault. So in the previous question, all the maximum values were given, whereas in this question, all the maximum values is to be calculated. Now combining all this, we are drawing the three cases. One is pre-fault case. It was 2.29 was the maximum power. Now during fault, the electrical power is 0. So there is no curve for that. Now third case is post-fault condition. Your electrical power is 1 point something, right? 1.5 per unit. So that is it here, 1.5 approximately. Okay, so that is the third case. Okay, so you have drawn the what do you call the power angle curve. Now the next point is marking the operating region. So what is the first operating region? This was the first operating region, right? Excuse me. This was the first operating region, right? A, where electrical power was equal to mechanical power. Angle corresponding to that is delta 0. So what happened at this point? Fault occurred. So what happened to your electrical power? Electrical power dropped down to 0. So now the electrical power is 0, whereas your mechanical power is 1. So what happens? Acceleration. The machine continues to accelerate and load angle increases, and let at this particular point the fault is cleared. When the fault is cleared, your electrical power is not 0. Electrical power will move to this next point in this curve. Okay, post fault curve. And the machine will continue to decelerate, but due to the what do you call the inertia, the load angle continue to increase till this point, which is a maximum value. Okay, so from delta 0 to delta CR it is acceleration, from delta CR to delta maximum it is deceleration. So what is our case? For transient stability, these two areas should be equal. So what is the first area? First area is from delta 0 to delta CR, PM minus PE. What is PE here? 0. Okay. Now the second case, deacceleration is from delta CR to delta maximum, PE minus PM. What is PE? Second case, third case. Okay, minus PM. Now let's see the two areas. These are the two areas. Here PE is equal to 0, and here in the similar way that we have calculated the delta 0 and the delta maximum, here also we have calculated the delta 0 and delta maximum. Then what did we do? We have the first area delta 0 to delta CR, PM minus PE. Here the PE is equal to 0, so it would be simply PM. Okay, so delta CR value we don't know. You have written like this. And the second area from delta CR to delta max, what is PE3 minus PM. Okay, so here what do you call, here you got the second area, and this was the first area, and this was the second area. Now for the system to be transiently stable, these two areas should be equal, and from equating these two areas you will be getting the critical clearing angle is equal to 55.8 degree. So actually, even though this type of questions are very lengthy, by properly analyzing this question and properly drawing this what do you call the power angle curve and properly analyzing this type of questions are very easy to score marks. Only thing is that we need to clearly identify which are the two areas, which is the accelerating area and which is the deaccelerating area. That's all. Then equate the two areas, you can calculate the critical clearing angle. Again, the suggestion or the request to all of you is that please do calculate it by yourself. Only then it would be much more clear to you. Otherwise, you just pan through this and you will you think that it would be clear, but while doing the problem, you will have some confusions or anything like that. So please do calculate this by yourself and compare with the results solved over here. Okay. So if you have any doubt in any of the sections in this lecture, please feel free to contact me or comment in the comment box. Okay. Thank you.